All right, here we are, core concept 8, and I think as part of further mechanics, paper 1 or part 1, this is probably the topic that is towards the end of that part 1, right? And it has two sections. I haven't decided whether both of them will be in the core section or I'll split them, but it's really about collisions, right? And we're going to discuss collisions in this section in one dimension, meaning you have just one line along which a collision occurs. This is probably the easiest area in the entire mechanics curriculum, and yet I think this is the best place for a test setting person like anybody testing, setting up a test or an exam to trick you. And this is probably where I think that I've seen more trick questions in this section than any other part of the curriculum, right? So hopefully we can work through it just as you do it. Remember to practice problems, practice as many questions as you can, even if it's just to get the calculation right, because it is a very tricky area, right? But we will jump right in, okay? So I've drawn here two things. So one is I have a particle, I've drawn it as a sphere, just a particle, treat as a particle, and a flat surface, and I have two particles, right? We've talked much earlier on in this series about particles colliding. We talked about momentum, change in momentum, all of those things. But what I want to address here is this. So you're going to assume that all collisions happen in a straight line, right? For the purpose of this video, they're all straight line collisions. There's no angles or anything of that sort, right? And we're not going to worry about, what the diameter of this particle is or anything like that. It's a point particle, straight line collision, okay? No friction, no air resistance. So purely an equation of mass and velocity and momentum and all of those beautiful things that we have done before. So we'll probably look at this picture first. Like you have two particles, okay? And you could have, and you know what, I'm going to call this, though the colors are different, I'm going to call it A and B, just to make it easier for us to understand this, okay? It's A and B, and we could have a scenario where A had a particular velocity coming in, U of A, right? And maybe it had one direction. And you could have a U of B, and maybe it had another direction, like that. Remember, it's not writing vectors, I'm just indicating the direction of this particle. And you could basically have a head-on collision. At the end of the head-on collision, you could have a returning with some velocity v of A, which is indicative of its later velocity, and you could have B going apart with some velocity v of B. That's a possibility. But you might also have a scenario where maybe B is really, really massive, right? And assuming that they have masses m of A and mass m of B, you could have a scenario B is really massive, A just knocks onto it and stands no chance and just goes backwards. You could have them both going in one direction. You could have an easy scenario of, say, final velocity v of A in that direction, and you could just have final velocity v of B in that direction, though the chances are both of them will be equal, but that's something we can think about later. But we could just have that, right? They just come together, and just one of them is so massive that the other just goes along, and they both roll together as one big mass. So we have all these different scenarios of what can happen, right? So for now, we're just going to keep aside all of those scenarios and just go to a very, very simple concept first to see. And this is something that has come out of, originally, it's an observational principle, which then got codified to say, if I see an object moving, let's say in this case it's a fixed object, so there's one object moving with initial velocity, right? It's going that way, and it's going to knock on this surface, and immediately third law of Newton kicks in, and there's a rebound happening this way with another velocity. Or we know, if in an absolutely perfect world, we would say it goes in and comes out at exactly the same, and if this was the particle's mass, a particle of mass m, then you know that m times u should be equal to m times v, because there is no effective loss, right? Or you might say half mu squared is half mv squared. It's literally not. But in reality, that doesn't. We know it's not true, and we know intuitively that as soon as you have a collision, there is a sound. So there is some amount of energy that's converted into sound energy, and sometimes there's vibration, which is other forms of mechanical energy. So in reality, it's never truly the same. It's never truly u and v being equal. There's always a ratio between them, and that ratio, right? So the final velocity v divided by u, and this is the important concept that we define here, is e, right? And that's called the coefficient of restitution. The coefficient of, quite a big word, restitution. I think I've spelled it right. Coefficient of restitution. In an average sense, it can be defined as the speed, because here I have two particles. And, in this case, the wall was fixed. So it was literally just, coming in and going out. But here I have two. So I could actually generalize this and say the speed of separation divided by the speed of approach. I'm always confused with these two P's. Is it one P or two P? I think it's one P. Watch it. Maybe it's my mistake. Maybe it's one. Right? In this case, you can see here, they're coming together. What is the effective speed of approach? If they're coming together, the speed of approach would be u of A plus u of B. You would think so, right? Because I'm traveling at the speed, you're coming from there at another speed. Effectively, our speeds add up. If we were parting ways, however, what do you think this would happen? Our speed should add up. But if after the collision, no, in this case, we were parting ways. I have a speed. If I was standing on top of particle A, it's my speed plus your speed because you're going the opposite direction. This would actually be VA plus VB. But that's why you're very careful. Because if this was happening, then it's not VA plus VB. Or in this case, if you assume, coming together, this one is 0, then you would get VA plus VB because it will be 0 on both sides. But here, if I was traveling in the same direction, for example, it's definitely not VA plus VB. It'd be the delta, the difference between the two. But we use the speed because we don't want a negative value, right? So we're going to first remove the vector component of it. Just know the direction so that we can perform either a subtraction or, so either that or VA minus VB, right? So because it's speed, note that word, speed, right? So this is one of the reasons why this is the most trickiest and easiest place for an examination to get you. Many students will make this mistake because the direction is very, very difficult for people to get. And I think this is an A. right? But you get it, you get the idea, right? So this is something to remember, the coefficient of restitution. So I'm going to just take this out for the time being. It's a very important point. Kind of go back to what are some of the interesting ideas that are going on here. So let's just take, you know what, before we go back into E, and think of it this way, right? If you had the case where a particle, after the collision, they move together, right? Now maybe this should be green. But still at separate velocities. Their final velocity. Imagine this case. So we've taken out the center case, is gone. Imagine this case is what happens after the collision. How would you map your momentum equation? You'd have to be careful because UA and VA are now in the same direction. So you couldn't just add that value of momentum, because that actually came because of the opposite velocity. You would have to make sure you adjust all of your directions, basically must add up. So however you choose your direction. So this is a very important area to remember. And the same applies here. If you calculate momentum going in and momentum going out, you should get a value for impulse, and you should be able to get some understand that the difference in the values is equal to impulse. So you should be able to get that too, right? So things to keep in mind. Let's go back to the coefficient of restitution now and say E. We know that you can never have your final velocity greater than that. So I mean, as long as it's a straight hard surface, there's no external force, you're not going to ever get, final velocity is not going to be greater than you at best case scenario, you can have V equal to U, in which case E is equal to 1, right? When V equal to U, or when speeds V divided by, so they approach and depart at the same speed, E is equal to 1. The obvious. Now what happens in another case where I take like a very ripe persimmon or tomato or something and throw it on the wall and it just smashes, and that's not going to rebound, smashes and effectively stays there. Or if you had two very loose objects that just kind of, like, I don't know, clay, soft clay, if you did soft clay balls, or maybe even balls made of snow, and then you had the roll, they just come together and just clump in which case you have initial velocity, you don't have any kind of final velocity, there's no velocity of separation, right? Velocity of separation becomes zero, so you get zero on the numerator and some initial velocity, some speed of, and again it's speed because there are two velocities in two directions, so we don't know. So the speed of approach exists, but there is no speed of separation. So E can actually also take the value of zero, and in reality, E is somewhere in between the two, right? So we often like to say 0 less than or equal to E less than or equal to 1, right? And we define this case as something is wrong with my spellings today, as a perfectly elastic case, and we define this case as a perfectly inelastic case. Just to make it neat, this is the number 1, and that's 0. So 0 to 1. And the reality is E is somewhere in between these two. And typically problems will either give you that and ask you to find a final velocity, or I give you the velocities and ask you to find the value of E, or they give you momentum, or they give you a function of impulse, or they give you energy. And notice that all of these have a relationship to velocity, and that's what helps you find out. Or they give you coefficient of restitution, which then you tie in with the impulse or momentum principles, conservation of momentum, or even the energy work energy principle, and you'll know. And the energy part, let's come to that first. Let's just, since I'm there, let's come to that. So what happened here? Let's say I'm coming in, let's say initial energy, kinetic energy. We're only talking kinetic energy. Okay, this is kinetic energy initial, I is equal to 1/2 mu squared. And final kinetic energy, so we just write Ke with a little f is equal to 1/2 mv squared. The difference between the two, so energy that is dissipated I'm going to get really confused with my spelling. Energy dissipated. Some people say energy wasted. And a few people will say written it as energy lost. But I never like this term, because energy ideally is never lost. That would be the failure of the conservation of energy. So it's never really lost. Some people will say it's a loss of mechanical energy. Some people will say it's a loss of kinetic energy, which is true, right? So remember these terms. It's never energy lost. It can be energy wasted because you drop, if I knock something, there's a sound. My hand, there's a sound. There's some amount of energy going to create that sound energy, right? Dissipation, yes. Sometimes in a very high impact, there's heat generated, yes. So all of these terms are valuable. But for the purpose of my illustration here, I'm going to use the term loss of kinetic energy is equal to kinetic energy final minus kinetic energy initial, which is usually just 1/2 m times v square minus u square. And you can do the math if you substitute in v as a function of u, or u as a function of v using the coefficient of restitution. You will now be able to say, for example, you know that v is nothing but ue, because e is equal to v divided by u. So you can now write this as, once it becomes eu square, you can take the u square out, and then you can write as 1 minus e, or the other way around. If v square, it's e square it's 1 minus e square. So you can do the math much easier given restitution, given velocity, as long as the collision is happening in one dimension and there is no, it's not turning around or anything like that between two particles. And you can do the same math by, instead of just v and u, if these v and u were just the differences, the velocity of approach and the velocity of separation, you calculate that between particles, you can do the exact same math and determine what is the loss of energy every time two particles collide, or every time a particle collides with a fixed surface. So that's another area to remember. Let me see what else comes in when we deal with okay, one other idea I think you might want to keep in mind. So all of this that we've discussed today are all, so if I can just, maybe I'll take that out. Okay, leave this one there. So it's another area, coefficient of restitution. So what is the other area? Is all of these collisions are called normal collisions. Normal collisions. And what exactly is a normal collision? A normal collision means if this is the surface and this is the direction of collision, it is perpendicular. This is 90 degrees. Remember this as well, right? Of course, if you're up to an AS level, you probably don't have to worry about it because all of the collision questions you might see will be normal. I think they only do the oblique collisions, as they call them, or non-normal collisions in the A level, and I think some of the high school curricula for physics have it, but typically they're all just normal collisions. But that is a term to remember. I just want to make sure I get through all the terms that you have here. Again, for the purpose of all of this, these are particles and not a sphere. They're all just particles that we're doing. Let's see. So we also discussed loss of kinetic energy. You have that. I think this is basically the fundamentals. Now I'm going to go to one other area, and then hopefully that should cover us for everything we needed for one-dimensional collision. Then we'll decide what we do with two-dimensional collisions later. So I'm going to take all of this away, right? So we can probably write that, we know. So that's the coefficient of restitution, right? So remember that. Let's just extend this, okay, to this time. Let's play with this a little bit. And this is where the physics gets really interesting. We have an object, and that object falls down. Now, if you knew the height, you knew the mass, we know that g is always constant, right? We know the value of g. That is 9.8 meters per second square, which means you can estimate the velocity v at this point, isn't it? So let me take all of this out. Take all this out. V. Experimentally, once the object falls down, if it was perfectly elastic, what would happen is, so this stays there, case 2, it would go up. So let me define here mv u equal to 0, right? And here it's just v. And that v can be basically is equal to a gt, right? That's just it. gt, that's the time it takes. And you can calculate the time because you know s. You can put that into s is equal to ut plus half gt square. You should get the answer. T is nothing but the square root of 2gh. So you can get that too. Very easy. Now you have a case where the particle now tends to want to go back up. Okay? Same thing here. This is equal to the new u, and you get v equal to 0, which then becomes the new u, and then you get v, and the cycle repeats. If it was a perfectly elastic world, but is that true? Is that what we would see? Highly unlikely. We don't see that, right? And don't say, oh, that's because there's gravity or that's because there's air resistance. It's really in small distances, the air resistance effect is very minimal, right? Gravity is always there. Even here, gravity is there because that's how I got GT. There's no gravity that wouldn't fall down. But in reality, we don't see that. What we see is something like this. The first case is valid, right? The second case goes up, but not nearly as high. And then in case 3, it comes back down that height. So this is the arrow. That's where it goes. This is where it comes back. And then it doesn't go all the way, it comes back here. and goes back all the way down. By the time we get around, and that's sort of where we end up, and it just kind of bounces down to rest. That's what happens usually. So why is that happening? Right? That's effectively happening because we don't live in a perfectly elastic world, and there is always a coefficient of restitution which is between this particle and the surface. Particle and surface have a coefficient of restitution E, and this is valid for that, it's valid for that. This is basically called successive impacts. Oh my God. Am I just going to make more mistakes? No, I got that right. Successive impact. This is an area, and I made it really simple because it's dropping on the ground and bouncing and comes to rest, as you would see, if you dropped a ball on the ground. But they love to put this into a problem with a horizontal movement with two particles. And imagine that if I gave you that, and I gave you two particles that collide with each other. When they collide, they'll go and collide against these two, and then they'll come back and collide with each other, and they could go that way a few times. So the same set of arrows needs to get drawn. That's another important thing that you need to pay attention to is, get the arrows accurately. In this particular case, we know it. We apply, for example, a V here, as in the same case, V is equal to GT. However, I do not equate it to U here because the new U for this phase, this is phase 1, this is phase 2, the U for phase 2 will be equal to, with coefficient of restitution, which is equal to, here was approach was V, separation divided by approach is E, so separation is equal to this value V of phase 1 times the coefficient of restitution. Now calculate the new phase 2's V2, right? Well, does that become phase 3's U3? Absolutely, because there is no restitution here, right? Because this will be 0, right? The value is 0. Now you come back down here and you'll get another value here. You apply the coefficient of restitution. This is basically whatever is this velocity is going to come back here, right? So it'll be VE, right? So this starts at 0, comes back here. It'll be the same as U2. Work with me on that. Make sure you understand this. If you've not, we've got to go back and do our S is equal to UT plus half GT square and play with them. But if this is U, this is 0, and starts with 0, comes back, it's U. When it comes down here, so this U2 is VE, this is VE. So it's coming back here with VE. And then here, your U4, phase 4, and you can use your own convention. Your U4 is equal to VE squared. Then that VE squared velocity becomes 0, starts at 0, comes back here to VE squared, begins at VE cubed, and you can keep going that way. So I've just shown you how the restitution basically, so if you had a 0.6 restitution, it's 0.36 here, and keeps successively reducing the velocity, and as it approaches 0, the ball stops bouncing and comes to rest. Theoretically, it just keeps going to 0.000, but in reality, when you multiply it, there is no noticeable change in the value of S. And when the value of this S or this H in your equation becomes, less than 0.01, you could safely say that the object has come to rest, and then you will know how many times, restitution has kicked in. But hopefully, successive impact, something that you'll also see, and they apply these problems into things like this. Remember the fact that you can always resolve them when you don't know velocities by checking for energy or by the conservation of momentum. Total momentum of the system is always unchanged, right? And energy is, understand the energy principle. If they tell you that, if they don't say that anything is, if they specify energy is lost, then they might ask you to find out the loss of energy occurring each time, and that's it. Very easy. Each time this is happening, I can say that there is some energy lost because I know how these velocities change with restitution. I can always say that, okay, every time it bounced up and down, there is a reduction in energy, which is basically E square minus 1. As that's the factor, and you can keep successively increasing that factor. You know how much energy is lost by the time, and then you can ideally come back here to see the original potential energy married to the number of times energy was lost for the ball to come to rest, and then it'll be ideally they'll come out to be equal. Though in reality, it's never truly equal because that you have to account for the loss in heat and vibrations and all of that. But yeah, hopefully that kind of covers all the major areas. So understand, how this is done, collisions that happen. The most important thing, coefficient of restitution carries a value from 1 at perfectly elastic, 0 perfectly inelastic. Understand that the collision can be between two particles or a particle and a surface, but when it is a surface, it is always a normal collision, right? Normal collision means it is perpendicular to the surface of impact, right? So in this case, this angle is perpendicular to the surface of impact, meaning the collision is tangential to that particle if you want to treat it as a sphere. But otherwise, just remember normal collisions. Maybe I write the term here, normal collision. Normal collision. So another area that you want to remember, successive impacts, another area to carry both with you, and how the coefficient of restitution changes. So there we have it, collision in one dimension. The most important parts of this has been covered. Okay, I'm going to create a small addendum onto this video, so I'll stitch it in at the very end because I think I made a mistake somewhere in the video, and I believe it was when I talked about the momentum equation. So I want to just go back to that area. It's very important because that's one of the ways in which problems get set. So what did we talked about two particles, let's just say A and B, right? And we had two particles coming in, and I think I might have told you that it's momentum, the conservation momentum is ma times ua, their initial velocity, right? Plus, and I'm guessing I wrote ma times va equal to mv. I think that I wrote the same for, I think I wrote mv ub plus MBVB. I think this is what I wrote, but I think this is not right. This is not right. Okay, so I made that mistake, so I have to address that. Okay, so let's just go back really quick and fix this. Okay, so we have mass of A, mass of B. We are given in approach, let's just say they're colliding with each other. That's what we're going to do here. But I want to show you the concept and tie it to, and this is coming in with a velocity UA, and this is coming in with a velocity UB. Upon impact, okay, they're going to move out. And in this case, you know what I want to do? I want to make this a little, just to get the directions correct. I want to say that that's going out with a VA, and that's going out the same way, B, with a VB. So at least the directions are right. So first things first, what is the principle of conservation of momentum? It is basically the total momentum of the system is unchanged. So that means you have to see the total momentum of the system just before impact, which is mass of A times the initial or the initial velocity of A plus the mass of B times the initial velocity of B, that's the total momentum just before impact, should be equal to the total momentum at after impact, which is mass of A times velocity of A plus mass of B times final velocity of B. That is the conservation of momentum. So I think in my previous, earlier on, I changed it, and that's again because even after going through this, going through the subject, the directions always mess me up. So this is really the conservation of momentum. This is what you need to remember. Total momentum is conserved, right? Now you can plug in the values you need. All right? Now let's also write the equation that relates to restitution, right? And they are both treated differently. Momentum is with velocity. Velocity is a vector with direction. The equation of restitution, or another term that I might have missed out, the law of restitution, which states that E right, that is equal to the speed of rebound or separation, speed of separation divided by speed of approach. Okay, so remember I told you speed, so that's valuable here. This is velocity. What happens with law of restitution? I'm going to grab another color here just so we get this part right. So we've got E. Okay, what would be the speed of separation? So here it's only speed, right? So we just need speed. When they're approaching each other, it would be the speed of, let's say, speed of separation. What speed of separation here? It's this. It's the positive value of the difference of these two, and we have to be very careful with it, right? Because you don't want to take it. If this one's 3 meters per second, this is 2 meters per second. Their speed of separation is still 1 meter, even though it's negative, meaning there will be a collision. At some point, they will collide again, but it is still. So just remember that part, right? That's very, very important. So this is the speed of separation of these two. So it's, let's say it's here, it's VB minus, you might say VB minus VA, and here you might just say UA plus UB, right? So remember that. Either way, you get an equation, right? But you have to figure out this. If VA was, and they were moving away from each other, this would be VA plus VB. This is important. Here, how do we do this? When you do this, you have to set a direction. You have to define this equation by making an assumption. Let, right, left to right be the direction. Be positive. Then when you fix this in here, you should be able to get MA, UA. UB is in the opposite direction, so it'll be minus MB UB is equal to VA, VB, all in the same direction. So this equation would be MA, VA plus MB, VB. That gives you the second relationship. This gives you one relationship. Typically, if there were equal masses, the M cancels out, and then you have a very interesting equation here. VA plus VB is equal to UA minus UB, and then you have another equation here, which is subtracting. You get the math by multiplying it. You can actually get the squares, and you can play around with these equations a fair bit. You have some unknowns. You can solve for one, substitute in the other, play with them, and you'll get the answer. So my biggest point, first, I wanted to correct this. That's The law of conservation of momentum. Total momentum system before, impact after. Might have made a mistake earlier, so watch that and ignore it. And then this part, when we talked about the coefficient of restitution, that relationship is called law of restitution. Some people call it Newton's law of restitution, Newton's restitution law, different names, but the principle is very simple. Get the speed of separation and then divide that by the speed of approach, and you'll get a value less than 1, less than equal to 1, and greater than equal to 0, and you're good. So yeah, that was the addition. See you in part 2.